Hello, this video is dedicated to gravitation, where we shall discuss about the famous Newton's law of gravitation as well as the planetary motions, the laws involving the planetary motions given by Kepler in association with Tycho Brahe. But before that, let us just consider what led to this entire thing or entire concept of gravitation. Well, to start with, the Indian astronomer Aryabhat, he had given in the 5th century AD the the conclusions that he had drawn about the planetary motion in his book Aryabhatiya. And in that, what he had mentioned is that the earth that rotates about its axis, he had mentioned about the rotation of earth, and also in that he had mentioned that the earth revolves. So the revolution of earth, this is about the axis, about its own axis, the rotation part, and revolution of the earth around the sun in a circular orbit or nearly circular orbit. Obviously, the earth revolves around the sun in almost circular orbit, although it is an ellipse, as we will be discussing later, but it's nearly circular. Now, later, towards the end of the 15th century or the 16th century, uh, or the beginning of the 17th century, there were Tycho Brahe along with Kepler. They had come up with the the laws that were governing the planetary motions, and popularly they are known as Kepler's law. And the first law being that all the planets move in elliptical orbit about the sun, and with the sun at one of its foci. Remember, the ellipse has two foci, plural for focus. So it has two focus points, and the sun will remain in one of its foci. The second one being that the radial vector from the sun to the planet sweeps an equal area in equal time, while the third one states that the square of the time period of a planet, that is the time taken by the planet to revolve around the sun, is proportional to the cube of the semi-major axis of the ellipse. To give you a picture of this, I draw an ellipse. We shall be discussing in details about these laws later on, but to give you an idea of what led to the uh, initiation of the theory of gravitation. So this is the elliptical path that is taken off by a planet. Let us suppose that dot that I am drawing over there. Let me just make it prominent for you. So this dot that I have over here is the planet. Let us say that is planet P, and this is an elliptical path, of course, and this is the major, while the other one being the minor axis. As the name suggests, the major axis is pretty large. You can see from the points, let us say from A to B, and the C and D is the minor axis, and the foci, that is the two focus, That's somewhere here. This is the sun of that for that given planet. It's quite large as compared to the size of the planet. So this is the sun. Let us keep the sun in this foci. There can be another foci over here, but the sun remains in one of the foci. So let's take the left one for our convenience. So now we have the sun in one of its foci. So this is the first law that we discussed. Now the second law states that the radial vector from the sun to the planet, okay, so the position that we can give is by means of a radius, and this is the radial vector from the sun towards the planet. And that vector, as the planet revolves around the sun, that, let us say, the planet is revolving along this direction. Uh, it's revolving around along this line, and as it is taking that path, this radial vector obviously sweeps a certain area. So the radial vector initially was here, now it's here, and there will be an area swept, of course, that I'm drawing by the that I'm giving the shading it. So that is the area, and that aerial vector that you see over there, because the area is a vector quantity, as we know from the vectors that we have studied about. So that aerial vector uh, per unit time must be a constant, that is del A by del T. So this law states that del A is the area swept per unit time has to be a constant every time, no matter if you find the area to be small or big. If the area is small, the time taken correspondingly will be small. If the area is big, then the time taken will be considerably large as well. So the thing is that the aerial vector, or the rate of change of aerial vector, is always constant for a planetary motion. And the third is that the time period, obviously it will take a certain amount of time, because it's a periodic motion, so it takes a fixed amount of time. So the time period, the square of the time period, that is proportional to the cube of the semi-major axis. Now the semi-major axis, this is the major axis from A to B, and let us say this point is O. From the point O to the point B, we have the value to be R. This is the semi, or the half of the major axis, and that value is R. So the time period is directly, the square of the time period is directly proportional to the cube of the semi-major axis. So these are the laws that they came up with, but they were not enough to explain everything. uh, then comes to picture the great man Newton. Well, Sir Isaac Newton, well, he was sitting idle in his uh, during the plague time. He was forced to sit in his home. Uh, that had the plague had broken out in Lincolnshire, his hometown, and that's why the Cambridge University, the Cambridge School, it was shut down, just like the recent times that we have come across during COVID. So at that point of time, they had plague, and during that plague, he was forced to sit in his home, and well, he came up with certain theories, and he came up with the concept that there's a force which is governing all the kind of motion that is happening around us, or the especially the planetary motions, as well as the earthly motions that were taking place. They were governed but by one law, that is the law of gravitation. Um, and it was a revolutionary idea that he gave to the world. To start off with, what exactly puzzled him is that the earth, the earth is at the center of the moon, and the moon revolves around the earth. The moon revolves around the earth in approximately 27.3 days. Let's convert it into the units that we have at hand. One day is 24 hours, and each hour has 3600 seconds. So this many seconds for our calculations, to be precise. And the distance between the earth and the moon is well, this distance is not to scale, of course. The distance is approximately 3.85 times of 10 to the power 5 kilometers. It's quite a large amount, not in terms of celestial distances. It's very small when compared to that. So this is approximately 3.85 times of 10 to the power 5, and let's just convert that into meters as well. 3.85 times of 10 to the power 8 meters, 1 kilometer being 10 to the power 3 meters. And if we obtain the acceleration, the angular acceleration especially, that is equal to the angular acceleration in this case is the centripetal acceleration, which is omega squared r. And omega squared r, omega is 2 pi divided by the time period, so 2 pi by t squared, and the distance r, right? So that gives me about 4 pi squared divided by t. As we know it is 27.3 times of 24 times of 3600 squared, and then we have the value of r, 3.85 times of 10 to the power 8. Now if you calculate this thing, what you end up with is that this is simply 0.0027 meters per second squared. So that's quite low, so as to speak, in terms of the numbers. Newton was concerned that what exactly is giving this force, and he also knew that the force was acting towards the center of the earth, because the moon is being attracted towards the center of the earth. Similarly, earth was also being attracted, but the earth was greater in mass and volume as compared to the moon. Later, the story goes that he found that as he was sitting under the apple tree, an apple fell down, and he observed that and it struck to him that the apple, well, to the general eyes, it may seem that the apple is falling down, but this is just to give you a diagrammatic representation of what happened. Newton was pondering about what was going on. He was sitting, spare my diagrammatic skills, but this is what somewhere he was sitting, and an apple, probably that size, that fell down, and to the eyes it may seem that the apple is just falling down, but to Newton, and as the genius of the guy, to him, he figured out that the apple was being attracted to the center of the earth, and that is exactly what he thought. And because he was Newton, of course, there were other apples in the tree as well, so we need not be concerned about them. They were not falling. Uh, but what concerned him was that what he deduced is that the laws that govern the attraction of the apple towards the center of the earth, apple to earth, the law that was governing it is the same for the moon to be attracted to the center of the earth. In fact, it is also the same for the earth to be attracted by the sun. So till that point of time, the world had not really accepted the concept that the laws will be the same for earthly and the heavenly, so as to say, objects. The earthly laws and the heavenly laws were deemed or were thought of to be different, but this was revolutionary in the sense that it unified the laws that were governing. Uh, as of now, you may have you may be thinking that this is quite simple, but at that point of time, we are talking about the 1600s or the 1700s. 1665 is when Newton was sitting at his home due to the plague outbreak. So at that point of time, this was not really that common, although it is common as of now. So he made certain assumptions, and his assumptions clicked. And what clicked is that few calculations that we can really consider with these kind of these kind of phenomenon is that the acceleration of the body that is falling towards the center of the earth, that's the gravitational acceleration as we have learnt till date, is 9.8 meters per second square, usually represented by the small g, and that is exactly the acceleration with which the apple is falling over the surface of the earth. So this is 9.8 meters per second square. What about the acceleration of the moon, which is doing the rounds about the earth? Now, the acceleration as we obtained for the moon, that was the angular acceleration, of course, but the angular acceleration here, if you multiply the radius, well, let me just rectify in case you have, in case I might have made a mistake over there, is that the angular acceleration, that's centripetal acceleration. V is equal to r, sorry, a is equal to r times of alpha, alpha by r. So this is simply the centripetal acceleration. So I'm making the correction so that we are not having any problems with that. Okay, that's done. I had written it above. The acceleration of the moon obviously obtained is 0.0027 meters per second squared, and if you take a ratio of that, you have the ratio. Let's do away with the equal to signs over there and just put it over here. Mm, just doing some rough work, so you need not be concerned about the cancellations and all that. So the ratio comes out to be nearly 3600 times. Well, the distance of the moon to that of the apple, which is falling, well, uh, you may think that the apple tree, the length of the tree is what the distance is all about, but that's not the case. The length of the tree is negligible when compared to the distance uh, with respect to the center of the earth. The earth is 6400 kilometers in radius, which is 6400 times of 10 to the power 3 meters, and that of the moon, as we just discussed in the previous page, is 3.85 times of 10 to the power 5 kilometers or 10 to the power 8 meters. Again, if you consider this ratio, that is nearly equal to 60 times, and this number what you can relate is somewhere there is a square which is uh, missing. The square of 60 is exactly equal to 3600. So what Newton guessed is that this acceleration that with which the moon is doing the rounds about the earth, or this force which is making it do these rounds, has an acceleration which is inversely proportional to the square of the distance. And because the force, by the second law what he has at hand, force is directly proportional to the mass times of the acceleration, then we have the mass multiplied with the acceleration, that is 1 by r squared. Now obviously the third law of motion states that the force on the body due to the earth must be equal to the force on the earth that is acting due to the body, and therefore this force should be proportional to the mass of the earth as well. So this force now has another mass associated with it along with the mass of that object, and this is the mass of the earth, this is the mass of the object. The object's mass is obviously lesser than that of the earth, so that's in small letters, so that's quite understandable. So this is what he ultimately came up with, that is, the force is directly proportional to the product of the masses of the objects involved. And then there has to be a dimensional or dimensionless, or maybe some constant which will make this an equation. It need not be dimensional, of course. So what he gave is just a constant g, and this is what the Newton's law looked like, and he named it gravity. Well, this g, we must appreciate or take time to appreciate the efforts made by the person, the uh, hero, so as to speak, Cavendish, in his experimental setup. After 71 years later, he obtained the value of this constant that was given by Newton. And it's an experimental setup which we need not discuss as of now, because it's quite in details, so that will be another video, of course. But the value is simply 6.67 times 6.673 times of 10 to the power minus 11. And obviously what you have is the unit. Well, the unit of force after named after Newton is N, Newton, and the R goes up right there, so this is Newton meter squared, and the two masses in kg can go down, and you have this to be Newton meter squared per kg squared, because the dimension on both the sides have to be the same. So obviously g must have this value, so that F is in newtons, and the other things have their respective units as well. Now usually what students or many of us can get confused with is that this value, mostly it is the same as that of the Planck's constant, which is 6.62 times or 6.63 times of 10 to the power minus 34. Forget about the powers in this case, but the value are quite similar. So how I understand it is that, let us take it, let's do away with that 3. 6.67 is simply 20 divided by 3. So I remember it this way, that 20 by 3, that is 6.67 times of 10 to the power minus 11, and there will be no confusion with this number, that is 6.63, because there are many whole lot of things that you have constant values with. Of course, in most of your books, or in even in the exams, they give you the value of constants so that you do not have to pressurize your memory. but it's good to remember these values with certain tricks that are at hand. And what I do is that 20 by 3 is simply 6.67. I remember it that way. The powers can obviously be remembered quite easily. Now, this is what the entire picture looks like now, that any two objects because the laws are the same for earthly as well as heavenly objects, any two objects m1 m2, and they are separated supposedly by a distance r, so they will have a force. Let us say that F12 is the force on 1 due to 2. This is a vector quantity, and that is equal to G m1 m2 divided by R12. R12 is the position of 1 with respect to 2. So what I'm doing is I'm doing it in the form of a position vector, R position vector of 1 with respect to 2. Well, these are just indices or numbers. You can put it in any way you like. It's not necessarily that it is the distance of 1 with respect to 2. If you say that R12 is the distance of 2 with respect to 1, well, that is your choice of words. That doesn't really matter. What matters is the ultimate result, but you must mention. So here I am saying that R12 is the position of mass 1 with respect to the second mass m2, and from that what we get is that this is F12, so the force on 1 due to 2, and obviously this is in squares, but the direction of the force will be R12. Now if if we are just capping it up, because this is the unit vector, and then what we can have is F21. F21 is the force on 2 due to the object 1, because conversely they will be applying forces on one another, and obviously the law does not change, that is gm1 times of m2 divided by r21. Well, that is the modulus and squared, but the unit vector now is the other way around, that is r21, that is the position of 2 with respect to 1. Remember, the position vector obviously is taken with respect to a certain thing. Position vector of an object with respect to a given object is just like in case of the origin. This was all in the vectors chapter, but just for your convenience. So this is an object which is a point P, and this is the origin. So the point P is having a position vector r with respect to origin. Now if the origin was to have a position vector with respect to P, obviously it will be the other way around vectorially, and it will be directed in the other sense. So from that point of view, what we can have over here is that F12 will be simply, it has the same magnitude of course, but it will be simply directed the other way around, and this is the concept of action and reaction forces, that is Newton's third law. And the as you can see, the directions in both the cases will be opposite. That means if m1 is attracting m2, so is the case with m2, which is attracting m1. Both the forces, as you can see, this one is attracting over along this line, the arrow that I'm just tracing again and again, and the other body is just attracting it like this. So what happens ultimately, let me draw it over here. If we are seeing a system where they have uh, separate positions with respect to a given origin, then the 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 forces will be acting centrally. Means one of the forces will be attracting the other object will be attracting the first object, the former. And as you can see, they are centrally placed, and so that is the concept of central force towards the center of mass of the system. So this is the concept of central force, and mostly the central forces are conservative in nature. The central forces that we come across, the central forces are conservative in nature. Well, the conservative forces are simply the forces which do work irrespective of the path taken to do the work. And that leads us to the energy that is associated with the conservative forces, and the energy that is associated with the conservative forces is generally the potential energy of the systems involved. So we'll be discussing about potential energy and the energies, so basically the gravitational potential energy and all the other things associated with it in the later videos on this topic. Till then, thank you for watching.